All right, so how you guys doing today?
Good.
Good. Perfect. Thank you. It's Friday, right? We're about to have a good weekend. So last time we talked about the person composition here. Person composition. It's 5 minutes. So we talked about the chemical formula, which you can see how many elements in your compound. So you can actually see maybe CH4. This is our methane. So it means in this chemical formula, in each methane molecule, we'll have a 1 carbon and a 4 hydrogen over here. Okay, and maybe sometimes you wanna find out how much of the carbon is here in methane by mass. This is when we're gonna do person composition for methane, the carbon in methane. Okay. So first of all, what you need to do is try to get the molecular weight first. So if you look at the periodic table, carbon will be about 12 gram per mole, or you can say 12 AMU. Okay, it's okay. And also hydrogen is about 1 gram per mole, or you can say 1 AMU. Okay. So if that is the case, you just need to count each element in the one compounds and try to add them all together. So we have 1 carbon, we have 4 hydrogen over there, 4. So in total, you have 12 times 1 is 12, and 1 times 4 is 4. So you have about 16 gram per mole, or you can say AMU for your molecular weight. So molecular weight of methane is about 16 gram per mole. Okay, so we got that number here. We just keep it. But if you want to find out the percent composition of carbon in the methane, we just get this one on the top. So 1 times 12 over, just copy the molecular weight at the bottom, 16. Okay. And then just multiply that fractional number by 100%. Okay. So in that case, this would be same as what? 3 over 4. So you will get 75% of carbon percent composition in methane. Okay. So what if we do this for the hydrogen? So it will be still the same. Okay. So this is a carbon percent composition in methane. So if you do for hydrogen, so hydrogen we have 4. So this is about 1. So 4 over 16 times 100 as well percent. That will give you 24%. So you can say the carbon percent composition in methane is at 75%, but for hydrogen will be 25% percent composition by mass. This is pretty much it. Okay. So let's do a little bit more bigger compound. Okay. So this might be another example. Okay. So we can try to do percent composition for each different element in the glucose. Okay, this is glucose. Okay, the glucose here. So chemical formula for this one will be C6H12. Great. Oh, you got someone already know this one. So this is the chemical formula for the glucose here, and try to find out what might be the percent composition of carbon. Once again, okay, we try to find out the carbon first. So when you try to find out the percent composition of some element in the compound, you just need to find out the molecular compound first. Okay, so we're gonna get the molecular weight for this one first. So carbon is, once again, there are 6 carbons in the 1 glucose, so it'll be 6 times 12 AMU. Okay, and hydrogen is once again 1, but there will be 12 hydrogen in 1 glucose. There will be 1 times 12. So it's all in the periodic table. This will be given to your exam. Don't worry about it. You just need to find it on the periodic table. That's it. But that is 1 times 12 because you have a 12 hydrogen in 1 glucose. And you have also 6 oxygen there too, which is 16. Okay. So if you do that all and try to sum it all to get the number for molecular weight, so there will be 6 times 12 is 72, right? And the 1 times 12 is just 12, right? And this will be 96, right? 96. Okay. So if you add them all, there will be the 180, right? Right? 180. Okay, good. So 180 ml approximately. Okay. So now we got the molecular weight. Okay. So molecular weight. We just sometimes just MW is molecular weight. So molecular weight of glucose is 180 gram per mole, or you can say AMU. And then now we got everything, but now we're gonna do it for carbon, so which is just this part. This is a carbon, this is the hydrogen, this is oxygen, right? So that is all 18, right? And the carbon part was 72, 6 times 12, so it would be 72 over 180, and same, multiplied by 100, okay? And then that will give you 40%. So meaning 40% of your glucose molecular weight is carbon weight. So the 40% of the molecular weight of glucose actually came from what? The mass of the carbons. Because you have this much of the carbon, weigh about 72, over the whole molecular compounds. And that is in percentile unit is about the 40%. So 40% of that weight is to the mass of the carbon. Okay? Makes sense, right? Just so it doesn't matter which one you go with it. If there was hydrogen, there will be 12 over 180. It was 96 over 180 for hydrogen and oxygen percent composition by mass. The only thing you have to change is number on the top. You can keep the always same number for the molecular weight at the bottom, and just multiply by 100%. Oh, and then in your exam, you can also have a calculator. So you just need to know how to set up the equation, then it's all done. But that's pretty much. Okay. Can I move on? Good. Okay. Perfect. Right. So there was a quick view on the person competition here. So when we have some chemical formula, okay, the chemical formula, I just showed you the chemical formula of glucose, which is C6H12O6 over here. And whenever you write the chemical formula for certain compounds, you can put it in the 2 different ways. Okay? The first one is the what we call molecular formula, which is just this one, the actual composition, actual numbers of each element in the one molecular compound. So we call this molecular formula. Each molecule has how many of each in that same compound. So it's a literally molecular formula. We have another one we call empirical formula. So empirical formula simply means once you have an actual molecular formula, you try to those numbers for each element by common multiple number. So if you look at this one over here, the ratio wise is actually 1 to 2 to 1, because they have 6 as a common multiple. So meaning if you try to divide each number by 6, that will become 1 to 1. So empirical formula will not tell you actual numbers of each element in the same compound, but the ratio. Why? So empirical formula for the glucose will be C1H2O1. Okay? So once again, the empirical formula does not mean there will be 1 carbon, 2 hydrogen, and 1 oxygen in the glucose. No. We do know there will be 6 and 12 6 in glucose. But empirical formula, we're only going to do it as a ratio. So the smallest possible integer number ratio. To do that, you need to have one good common multiple number and divide those all numbers in the molecular formula so you can get the empirical formula. So let's do one more. Okay. So if we have C2H6, okay. So this is this is ethane, right? And if this is ethane, the molecular formula for this one will be C2H6, because that means there are going to be 2 carbons having 3 hydrogens on each. There will be 6. But empirical formula wise, we can try to find that what might be the common multiple for 2 and 6 will be 2, right? So then we just try to divide this number by 2 and 2. So molecular formula for ethane will be C2H6, but the empirical formula for ethane will be C1H3. So empirical formula does not mean actual numbers of each, but just simply is the ratio between elements in the same compound. So this is more accurate on the actual numbers of each, but this is to be more easier for us to use when you just wanted to look at the ratio between different elements in the same compounds. Okay. That's pretty much it. So maybe if I give you maybe C3 H maybe 9O3. Okay. Maybe if that is the case, common multiple number will be what? 3, right? So then we can just put C1H3O1. Okay. In that case, this is a molecular formula. This will become your empirical formula for the compound. Okay. It's pretty much the same thing. There's one tip you can find the. So maybe you can try to do this. Okay. In this case, okay, if you have a certain numbers looks like this one, I just made it up, but if that is the case, maybe just change this one to. This will be more realistic. Okay. So anyway, if you do this one over here, the easiest way to find out the empirical formula is look at the numbers on each, okay, and pick the smallest one. Okay, most of the time there might be the common multiple, and like a 90 or 80% chance. So then you can just do 8 divided by 4 will be 2. 16 divided by 4 is 4, and 4 divided by 4 it will be 1. That's it. Okay. So most of the time, this will be just easiest possible way. You can just get the empirical formula right away. Okay. All right. So but now you guys know. Yeah, go ahead.
You just write the oxygen as just oxygen, correct?
Yeah, just the C8H16. So in this case, try to find the smallest number and try to divide that each number by the smallest number you see, and that will get you a very easy way to find the empirical formula. That's the one way to do it.
You don't have to write the 1 below the oxygen.
Oh, you don't have to. You don't have to. 1 is usually ignore always. If it's higher than 1, yeah. Makes sense, right? Good, perfect. All right, so if that is the case, this is kind of not a very, but I'm gonna warn you, what we're gonna do now is one of the most difficult topic in Gen Chem 1. So I want you to listen to me very carefully today, okay? So you guys remember stoichiometry, right? Stoichiometry. So we haven't got to that topic yet, but I'll try to explain the quick review on this one. So stoichiometry is simply whenever you have reactions, okay? The one on the left is the reactants, right? Remember? And the one on the right is the products. So this is the outcome of the chemical reaction. This is the starting material. and they're going to interact each other to react to each other, so to make two products or one product and so on. This is the one you're gonna write on the right side. The one you start with is on the left side, right? And then it's all about the stoichiometry. Spectrodynamic means you have a quantitative analysis. So quantitative analysis means you need to find out how many. This is very important in this the stoichiometry. So that's why we put this in the metric at the end. Metric simply means you're gonna quantifiable data, so you're gonna use it for your chemical reaction. So meaning the most important job for the using stoichiometry when you look at the chemical reaction here or chemical equation here, you just need to find out how many of each these two will make how many of the two product over there, which we kind of did when you try to balance the chemical equation. So the one we did so many times before, the balancing the chemical equation was combustion reaction of the organic compounds. Okay, combustion reaction of the compounds. Okay? So you're gonna have a CO2 and H2O. This is the two products you can expect from the combustion reaction of the organic compound. Okay, so we have one here. So we can just try to do this. We just try to balance the numbers of carbon and hydrogen on both sides. And so we have a completed chemical equations on here. So if you have a one methane and two oxygen molecules, you have a one carbon, four hydrogen, and four oxygen on left side. So if we do also 1, 2 over here, you're gonna have a one carbon, four hydrogen, because it's two, but there's two hydrogen each water, so it'll be four hydrogen as well. And one carbon dioxide has two oxygen, one water molecule has one oxygen, but two, so it'll be 2, 2, 4. Here's a four oxygen, two, one carbon, four hydrogen, all same. So it's now it's done, right? So whenever you're done with the balancing the chemical equations, now you're ready for the stoichiometry now. So whenever you look at this 1, 2, 1, 2, it's simply number, right? Number. It means that one methane will react with two oxygen dioxide molecules to make one carbon dioxide and two water. Okay, so that means if you have a two instead, not one. Okay, so you know there will be one methane, two oxygen will make one carbon dioxide and two water, right? If you have a two methane and if you have a four oxygens, right? Now you know that will make also double amount of product as well. It's just the number by number, right? If one can make two, two can make four. Because it's all about the stoichiometry, right? Makes sense, right? Okay, that makes sense, right? The number, okay, good. So if that is the case, I just wanna start with the Avogadro number. So as you know, if you look at the chemical equations, there's like one or two, but it's very small compound, very small molecules. So whenever you look at this in the like a macro scale, like in a real like a chemical experiment in your lab, you're dealing with lots of numbers of each, not just 1, 2, 1, 2, right? That 1, 2 simply means just the ratio. Like 1 goes in, 2 means the same as 10 goes in, make 20. It's the same. It's just about the ratio, but not actual number. But to be more realistic, we're gonna use the Avogadro number. So Avogadro number is about 6.022 times 10 to 23rd per mole. Okay, so that means this one. If I have a 1 mole of methane, if I'm saying there's 1 mole of methane, meaning this is the same as I have 6.022 times 23rd numbers of the methane. That's what it means. Okay? But obviously, if you say I have a 1 mole of methane, it's much easier to put instead of saying there is 6.022 times 10 to 23rd numbers of methane, right? It's much easier to say. And this is more realistic because this is about the more realistic number over here. So we got the Avogadro number by simply using carbon 12. So if carbon 12 is about 1 mole, if you have 1 mole of carbon 12, that is exactly 12 grams. Because this is our standard. So we got this Avogadro number from the carbon 12. So if you have a 1 mole of carbon 12, that's exactly 12 grams. That is why I keep telling you in the previous lecture, either you can say 1 AMU, 1 gram per mole is the same thing. Because if you look at this one over here, if you have one mole of methane, is the same as you have a 1 mole of carbon, right? Also, you have 4 moles of hydrogen. Because if you have a 1 methane, you automatically have a 4 hydrogen there, right? So if you have a 2 methane, that means you have a 8 hydrogen. And then if there's 1 mole of methane, means you have 4 moles of hydrogen in the compounds. Because each methane carries 4 hydrogen. Okay? Makes sense, right? So if you do carbon, that is 12, plus not 1, but 4 moles of hydrogen, which is the 4 times 1, that will give you 16 grams per mole. So meaning, if you have a 1 mole of methane, it will weigh about 16 grams. So that's why we put that number 16 gram per mole. So 16 gram per mole means simply, if there is 1 mole of something, this is how much does it weigh. It weighs. So it kind of makes sense. You have a 1 mole of carbon will weigh about 12. 1 mole of hydrogen will weigh about 1 gram, but you have a 4 instead. That's why we did this previously. 16 plus 1 times 4 is 16. That is its molecular weight. This is what we did last time, and this is why. Because the Avogadro number is the one that we use for making actual grams of something. And there is the numbers of that, you can multiply the numbers of the elements. So in total, the weight is molecular weight. That's what we've been doing with a much bigger number, which is Avogadro. So so Avogadro number simply means a very big number, right? Very big number. Okay? So I kind of want you to remember this one. Mole is not a unit. It's just a big number. But you don't want to say it's like, if you have, could you tell me what's this one? What is this one? It's one, could you read this one for me? It's 1 million, right? No one gonna read this number 1,000 or 1,000, right? Because the million is much easier way to say it, the same number. The 1 mole is the same thing. You don't want to say every time 6.02 to 10 to 23rd. Just say 1 mole. It's much easier that way. Okay. So mole is not a unit, just big number. Doesn't mean any physical property or anything, but just simply a number, just a number. Kind of makes sense. We good? Okay. So let's do the dot here. So if that makes sense, let's do a realistic problem over here. So if you have, for example, you have 16 gram of methane in the lab. So you're gonna burn the 16 grams of methane, and you find out there might be in the fume hood. You find out there are like maybe 40 grams of oxygen there. Okay, so you estimate there's 40 grams of the oxygen over there, and you just need to try to find out how many grams of these two will be produced. Okay, so this is your job. So now you're going to very realistic problem now. This is something you always do in the chemistry lab. It's every day. So if you look at 16 gram over here, what you can do is, this is the actual mass, right? This is what really, how much that weighs in the lab, okay? This is 40 gram actual mass too. So you put this number, actual mass, which is 16 gram, on the top, okay? And then you divide that number by molecular weight of methane, which is 16 gram per mole, okay? So if you look at this one here, this is 16 gram per mole, once again, because the 1 mole of methane will weigh about 16 grams. But actual mass of the methane is also 16. What did it tell you? You know the 1 mole of methane will weigh about 16 grams. But now you have a 16 gram exactly. That means you have 1 mole of methane. It's the same thing. Okay? So now you have, so what happens to this one is this gram per mole, if you can cancel those 2 units, top and bottom same, and you can get this number on the other side as a numerator unit. So it makes 1 mole, right? So if you have a 16 grams, that means you have 1 mole of methane. Okay? Makes sense, right? Okay. So if that is the case, O2 is the same. So O2 means there are 2 oxygen. So maybe 2 times 16, which is oxygen is about 16, right? It's a 50.99 something, but just make it 16. It's about 32 gram per mole. Okay. Meaning, if you have a 1 mole of oxygen diatomic molecule, they will weigh about 32 grams. Okay. But you have 40 grams over here. 40 grams. Okay. So if you do 40 grams. So I'll do the same. 40 grams, which is actual mass, divided by molecular weight of the oxygen gas molecule, which is 32 gram per mole. Okay? And then that will be approximately, that was the 8, 5, 5. Am I right? Yeah. So you get about this many moles. Okay? Makes sense, right? Okay. So you have a 40 grams, but this is the how much does it weigh when it's 1 mole. So if you divide actual mass by molecular weight, you get the how many moles you have over there. That is about 1.25 moles. Okay? 1.25 moles. Okay. So now you know you have a 1.25 moles over here. Okay. So here's the problem. Whenever, so think about it. This is about ratio, right? Whenever you have a 1 methane, you need to have a 2, right? You have a 1 mole of methane, then how many moles of oxygen do you need to have? 2, right? But so you're supposed to have 2 to make this 1 mole of methane going into full 100% combustion reaction, right? But you only have 1.25 moles, right? So that means between these 2 reactants here, this is a reactant, this is another reactants here. This is what we need more. This is what limits the real full reactions here. So this is what we call limiting reactants, or you can say limiting reagent. It's the same meaning. Okay, because this is the one that limits the full chemical reactions. So if you have limiting reactants over here, the other one is what we call, there's 2 ways to say it. You can say abundant reactants, or you can say excess reactants, meaning they're too much. They're too much, relatively speaking. Because from this view, it has 1 mole, so it should have 2 moles of a carbon, I'm sorry, not carbon, the oxygen gas molecule here, but only 1.25. So meaning, let's just look at from this side. If you looking at from the oxygen, it has a 1.25, right? Okay, so you only need to have just 2.5. No, it's the 1, 2, 6, 2, 6, 7, 5. Okay. There's 2. Okay. There's 1, 2. Just make sure. Okay, so you need to have only half of a 1.25, but you have 1 mole. So from this view, you have more than what you need. That's why we think this is abundant reactants or excess. Okay, kind of makes sense. Okay, so if you know which one is your limiting reagent now, only thing you have to do, you stick to this one, because this is the one that is going to be 100% used. This 1 mole of methane will not be used 100% because it's abundant. But this is the one that limiting the reactions. This is going to be the one that fully used. Okay, so now this is going to be your number that you can use for stoichiometry. So if that is the case, look at this one. You have a 1, 2, makes 1, 2. Meaning, if you have a 2 oxygens, will make 1 of the carbon dioxide and 2 water. So if this is a limiting reagent, you're going to have a 1.25 moles will be all used up, and it makes also 1.25. There are 2 moles of the carbon dioxide and 1.25 moles of water. Because it's 2 to 1 and 2 to 2 means it's the same, 1 to 1. Okay? So if that is the case, you can try to get each moles of this one. So 1.25 divided by 2. Okay? You can try to do this. So that will be 0.625 moles of carbon dioxide will be produced. Okay, and then same numbers of moles of this one and this one will be produced. Will be 1.25 moles of water will be produced. Okay, makes sense, right? Does it make sense? Here's the thing. So between these two, this is the one that will be fully used. Okay, this won't be used all 100%. So now we stick to this one. You don't have to worry about this one anymore. Okay, and this one, if you have a 2 oxygen molecules goes in, make 1 carbon dioxide and 2 water. So that makes half of the actual moles of this one for carbon dioxide, and same moles of the water will be produced. Yeah, that's it. Kind of makes sense, right? Okay. So if that is the case, you just need to, it's very simple now. You have a 0.625 moles of carbon dioxide and 1.25 moles of water. You just multiply this number by its molecular weight, and you have the answer. So carbon dioxide is 12, and there will be 16 plus, multiplied by 2, which is 30. 2 plus 12 is 44, right? So 0.625 times 44 gram per mole, okay, which cancel the moles top and bottom, and you get the numbers in grams over here. And 1.25 moles of water, which is 1 times 2, which is 2 hydrogen, and 1 oxygen will be 16, it will be 18, right? So you multiply 1.25 by 18 gram per mole, you get the numbers in gram too. So then you can find out how many grams of each product, which is carbon dioxide and water, will be produced there. So the yeah, so it's kind of a lot of long way to work, right? So let's do one more, okay? Do we have time? Oh yeah, we have 5 minutes, so we can do one more. And like I said before, this is one of the most difficult part in Jenkins 1. So I'm gonna spend very long time on this one, on also next week as well. So this is a very long process. So I'll try to do it more easily. So let's try to make it more complicated than this one, okay? So more complicated, this one would be, maybe you can use propane. Okay, use propane, oxygen. Okay, so you can have also combusting organic compounds over here. So we have a 1 over here, that has to be at least 3, right? And 8, there has to be at least 4. So that makes a 6 oxygen here, that makes 4 oxygen here, so it has to be 5. Okay, so it has to have a 5, right? So now it'll be 1, 5, 3, 4. That is the ratio. So you can assume that is the ratio between 1, 5, 3, and 4. So you can call this the molar ratio. Means it's the same. That's the ratio between these two by number. Because mole is simply just a big number. So we normally call this molar ratio because it's more realistic when we put the numbers in mole. So you can have a more realistic number. But anyway, so if this is the case, it's not simple because it's not 1, 2, 1, 2. It's 1, 5, and 4, and 5. 1, and 5, and 3, and 4. So in this case, what you can do is this one. You try to get this one of this either way. Just try to pick one of this. It doesn't matter. If you choose this one, it's okay. But maybe let me choose this one first, okay? So try to get the molecular weight of this one. So there will be 3 carbons. So 12 times 3 plus, you have a 1 times 8 because you have an 8 hydrogen over there, right? So that's 36. 12 times 3 is 36. And obviously it's 8, right? 1 times 8 is 8, right? And then we'll get with 44 grams per mole, okay? So molecular weight of the propane is 44 grams per mole, okay? And we already did this one, right? We already did this one over here. This is 20. This is 32 grams per mole, okay? Over here. So when we get this one here, only thing you really need to know is whenever you have one moles of the propane, you need to have not 2, 5. So 1 propane need to have 5 oxygen molecule, right? Because it's not 1, 2, it's 1, 5 now, right? In that case, for example, we have indeed 44 grams. Okay, that makes really easy calculation for us, right? So let's say we have 44 grams exactly for propane. Okay, and then you can actually calculate how many grams of oxygen you need to have by using molar ratio 1, 5. So this is what you can do. This is what you're comparing to, right? So you have a coefficient number 1 and 5, and try to compare 1 to 5, right? So the coefficient number you're comparing to goes on the top. Okay, remember this one. So you have you're gonna compare the propane to oxygen, right? So the one that you're comparing to, the coefficient number goes on the top, and then you compare that to the one you started with is at the bottom. So this is 1 to 5, but this is what you compare to, so it'll be on the top, this is the bottom. So it'll be 44 grams times 5 over 1. Okay? Then you can do this one, right? So meaning, if you have 44 grams of propane, meaning 1 moles of propane, you need to have, I'm sorry. I'm sorry, this one. So this, not 44, we have a 1 moles of methane, you need to have a 5 moles of this one, right? Okay? So then you have to have this one, because each mole of oxygen will be evaluated this one. So if you do this one, you're going to have this number. Okay, because you need to have 160 grams of oxygen can be fully 100% interact with 44 grams of propane. Because you need to have 5 oxygens to interact with only 1 propane. So if you have more than 160 grams, this will become your abundant. If you maybe for example, if you have only 100 grams of oxygen, this is going to be your limiting reagent. And it's vice versa too. Okay, kind of makes sense. Because so this is what you need to find out, right? How much you need to have for propane. That's why we use this number for oxygen diamond molecule, and it has to be 5 times more of the propane, so it's 5/1, and this is the actual mass you need to have for making this reaction 100% completion. So if you have a more than 160 grams of oxygen, this will become abundant. If you have less than this number, this will become limiting. So if it's 200 grams of oxygen there, this will be limiting then, because this will be all used up. There will be some left over of the oxygen will be still there after chemical reactions. But if it's less than 160, 120 grams, this will become your limiting. Okay? I'll stop here, but trust me, I'll do this again on next week. So you can also watch it on the YouTube channel. Make sure you guys keep watching the YouTube channel video. Or you can also come in the lecture if there's enough room. But I'll definitely do this again. Don't worry about it. I understand this is one of the most difficult topic on the Jenkins one. So let's spend more time on this one, okay?